At first light, a flat-top mountain does not look ancient. It looks interrupted. A dark mass rises from the valley floor, with sides so abrupt they seem cut rather than weathered, and a summit so level it resembles a surface left behind after something larger was removed. From a distance it reads as geology. Up close it reads as an object. The walls run almost vertically for hundreds of feet. The top sits there like a sealed plain. Around the base the land falls away in aprons and channels, as if material once surrounded it and no longer does. This is a familiar landscape in many parts of the world: a mesa, a butte, a table mountain, an erosional remnant. That is the official language. But standing beneath one of these forms, another question arrives before the explanation does. What exactly are we looking at? However, the accepted story is clear, and in many cases it is persuasive. Vast layers of sediment were laid down over immense spans of time. Later, uplift exposed those layers to water, wind, freeze, heat, and gravity. Softer rock wore away first. Harder rock resisted longer. The result was differential erosion, isolated mesas, buttes, and flat-topped highlands left behind from plateaus that once extended much farther. In the same broad historical timeline, the Earth's first forests appeared in the Devonian and spread across the Carboniferous, filling swampy lowlands with giant club mosses, horsetails, ferns, and early trees. Their remains were buried, compressed, mineralized, and in many regions transformed into coal, shale, and scattered fossils. Forests became seams, mountains remained mountains. The categories stayed clean. Biology on one side, geology on the other. For more than a century, that division has governed the way the landscape is read, and yet there is a problem with how clean that division feels. Some flat-topped mountains do not merely look resistant, they look specific. Their outlines are startlingly discrete. Their sides are sometimes furrowed in long vertical grooves, as if the face once followed an internal grain. Their tops can appear sharply planar even where surrounding strata are broken, tilted, or irregular. Around them lie basins filled with carbon-rich sediments, silicified fragments, coal measures, root-bearing horizons, and the debris of vanished wetlands. In photographs, some stand not as fragments of a plateau, but as singular columns widened at the base and cut clean at the top, how it's like forms preserved after the surrounding mass was stripped away. The official explanation can account for much of this, but it also asks us to ignore how often these landscapes resemble not just eroded rock, but the lower remains of something once organic, once upright, once part of a larger living system. The resemblance alone proves nothing. What matters is whether the record around it deepens that resemblance into a pattern. The hidden theory is not that every mesa is a tree, or that geology is an elaborate fraud. It is narrower, and in some ways more disturbing. It suggests that a portion of the Earth's oldest forested world may survive in forms we no longer classify as biological at all. Not as standing trunks in the ordinary sense, but as colossal basal remnants of a carbon-rich biosphere that was buried, chemically altered, and compressed, mineralized, and later exposed by erosion. In that reading, some flat-topped mountains are not simply leftover plateaus, they are reclassified ruins. Their organic origin, if it existed, has been overwritten by the language of rock mechanics, stratigraphy, and deep time. The theory sounds strange because the scale sounds wrong, but scale is often where categories fail first. The first forests were not modern forests. They belonged to another atmospheric regime, another ecology, another chemistry of growth and burial. What changed was the explanation. Begin with shape, because shape is where the discomfort starts. A typical erosional remnant is supposed to preserve the geometry of the layers from which it came. That is the principle. Yet many flat-top mountains and isolated buttes do more than preserve layers. They present a recurring physical grammar, a broad circular or oval crown, abrupt wall faces, fluted vertical sides, tailor skirts at the base, and drainage patterns that radiate outward as if from a central mass. The proportions matter. In some cases, the diameter of the summit is far greater than the height of the exposed wall, a ratio more suggestive of a cut base than of a surviving tower. In other cases, the summit edge is beveled, almost like a weathered growth ring, while the sidewalls descend in ribbed segments that do not read as random collapse. Geology calls these joints bedding planes, resistant caps, erosional benches. Fair enough, but when the same form appears again and again, the eye notices something older than terminology. As it notices that these mountains often resemble stumps more convincingly than they resemble the fragments they are said to be. The pattern is visual before it is theoretical. The stone remembers. Then consider where many of these forms stand. They are often surrounded by lowlands made of finer material: mudstone, shale, soft sandstone, coal-bearing strata, unconsolidated debris, or soils built from weathered sediment. In plain terms, the giant isolated mass sits inside a basin of softer stuff. That is entirely compatible with erosion, but it is also compatible with burial. If an enormous upright biological structure were encased in catastrophic sediment, later mineralized and later exhumed, the surrounding field would not necessarily preserve its original arrangement. It would preserve the fill. However, around many coal basins and ancient swamp deposits, what remains is not a neat ecological picture. It is a compressed archive of transport, pressure, chemistry, and removal. Fossil roots appear below one seam, driftwood above another, marine incursions interrupt terrestrial deposits, and thick accumulations of plant matter are folded into sequences that speak less of slow forest litter and more of repeated burial. The official explanation calls this normal basin development over long spans of time. It may be, but the same record also leaves room for another possibility, that some of the largest biological forms did not become coal seams or scattered petrified logs. Some remained as cores. The accepted history of the first forests actually makes this possibility harder to dismiss than it first appears. Only those forests were unlike modern woodland. They were dominated in many places by plants with unfamiliar architectures, rapid vertical growth, shallow rooting, hollow interiors, bark-heavy tissues, spore-based reproduction, and enormous dependence on wet lowland conditions. Lepidodendron and sigillaria rose like columns, calamites formed jointed thickets, tree-sized lycopsids built entire landscapes with tissues that do not map neatly onto modern wood. Add to that an atmosphere with different oxygen levels, climates with widespread wetlands, and continental interiors that could accumulate staggering volumes of organic matter. None of this proves mountain-scale growth. It does something more important. It breaks the instinct to imagine the ancient biosphere in the size limits of a modern pine forest. The record already tells us that the first forests operated by rules that feel alien now. Their remains became coal, black shale, petrified trunks, seat earths, rooted layers, spores, amber-like residues, and mineral templates. Mineral replacement is not controversial, silicification is not controversial, massive burial is not controversial. Only the scale is controversial, and scale, in this case, is precisely the point under dispute. There is another clue in the surfaces themselves. Look closely at many flat-top mountains and isolated towers, especially where vegetation is thin and the walls are exposed. The sides often show long parallel channels or ribbing running from summit toward base. In geology, these can be explained by jointing, differential weathering, runoff incision, and the tendency of rock to break along pre-existing planes of weakness. That explanation is real, but it does not erase the resemblance. Some walls appear fibrous, some appear segmented, some show a layered outer shell with a more massive interior, as though the exterior weathered differently from the core. In ordinary petrified wood, one of the striking features is that original biological structure can survive complete mineralization. Grain remains visible, growth boundaries survive, cellular architecture can be replaced molecule by molecule and yet retain form. Scale that process upward far beyond accepted limits and the idea becomes uncomfortable but not conceptually impossible. If a colossal organic column were mineralized and then stripped of surrounding fill, what would the exposed side look like after millions of years of weathering? Not like fresh bark, not like wood. It would look like rock that still carries an older order inside it. The official explanation describes the mechanics. The hidden theory asks whether the mechanics acted on something we have misidentified from the beginning. Old names matter because they reveal what people saw before categories hardened around it. Across continents, isolated landforms were called table mountains, towers, chimneys, monuments, castles, pulpits, and stumps. Stump is the word that keeps returning, sometimes informally, sometimes in local naming, sometimes as a comparison in early accounts. That does not make the comparison true. It does show that the resemblance is not an internet age invention. 19th century surveyors, photographers, railroad men, and settlers repeatedly described landscapes in architectural and biological terms before modern geomorphology settled the matter into standardized labels. Early photographs are especially unsettling because they strip away the comfort of lush vegetation and tourism imagery. In those images, the land looks raw, excavated, skeletal. Flat tops read as cut plains. Sheer walls read as exposed sections. The surrounding country appears scoured or dumped over rather than gently evolved. The language came first. Then the explanatory system arrived and told everyone what they were supposed to be seeing. The record is still there, not hidden, just translated. To be fair, the mainstream explanation deserves its strongest form. Resistant caprock absolutely can preserve a summit while softer rock erodes away. Horizontal strata absolutely can produce mesas and buttes, volcanic intrusions, welded tuffs, quartzitic caps, sandstone ledges, and basalt tables all create flat-topped relief. Columnar jointing can mimic fibrous structure. Freeze-thaw cycles and runoff can carve near-vertical walls with astonishing precision. On any honest reading, many flat-top mountains are exactly what geology says they are. The problem is not that the standard model explains nothing. The problem is that in certain cases, it explains only the final stage. It explains how a form persisted, not necessarily why that form existed to be preserved. A caprock tells us why the top survived. It does not always tell us why the surviving mass is so isolated, so abrupt, so singular in a basin that otherwise feels stripped. Stratigraphy tells us what materials are present, when it does not always resolve whether those materials filled around an original upright form or simply remained after everything else vanished. Mainstream geology answers the question it is trained to ask. It can be less interested in the question beneath it. What happens when the scale widens is even more revealing. The same visual grammar appears in separated regions governed by different local histories, the mesas of the American Southwest, the buttes of the Northern Plains, the tepues of South America, table mountains in Africa, isolated caps in Australia, fortress-like erosional towers in Asia. No serious investigator should claim that all of these share one origin. Their lithologies differ, their ages differ, their tectonic settings differ. But the repeating silhouette still matters. Again and again, the Earth presents broad, flat crowns on abrupt masses standing above lower terrain as if the surface of a once higher or once fuller world had been shaved away. Again and again, those forms occur amid sedimentary archives, rich in water transport, burial, mineral exchange, and biological residue. Again and again, the official explanation changes in detail while the profile remains strangely familiar. Intrusion here, remnant there, escarpment elsewhere, the labels shift, the shape does not disappear. That is how hidden patterns survive, not by being invisible, but by being explained differently each time they appear. Now place those forms beside the timing of the ancient forest world. The late Devonian and Carboniferous were not quiet chapters in Earth history. They were periods of ecological expansion, atmospheric change, coastline migration, repeated flooding, time anoxia, delta building, basin subsidence, and enormous organic accumulation. Whole landscapes were drowned, buried, compacted, uplifted, and buried again. Coal measures speak of forests, but not of a peaceful forest floor left untouched. They speak of vegetation overwhelmed by sediment, of peat masses sealed under pressure, of waterlogged systems transitioning through chemistry into stone. In many places, the record is broken, repeated, truncated. There is evidence of roots where trunks are gone, of trunks where canopies are gone, of spores where entire ecosystems have been erased. The first forests are known largely through fragments, impressions, and converted carbon. That is the accepted record. But if the record is already one of destruction, compression, and replacement, then the disappearance of larger structural forms is not the improbable part. The improbable part is our confidence that nothing of that scale could survive, except in categories we already recognize. There is also the matter of missing infrastructure. A flat-top mountain is commonly described as the remnant of a once continuous plateau. Sometimes the surrounding terrain supports that beautifully. Adjacent scarps match. Layer sequences continue. The case is strong, but in other places the implied vanished plateau is strangely absent as a practical landform. The surrounding low country does not always preserve a convincing intermediate geometry. Instead, there is a singular tower or isolated mass rising from basins that look more like fill plains than shaved highlands. The supposed former connections are theoretical reconstructions drawn from strata, not necessarily from the lived shape of the terrain. That distinction matters. A basin of soft material around an isolated resistant core can be explained either by widespread erosion or by widespread deposition later removed. The first model is standard because it uses the accepted toolkit. The second model starts to sound biological only when one notices how often the isolated core resembles the base of a removed vertical system. And once that possibility is seen, other details begin to acquire weight: circular drainage, ring-like benches, carbon-rich debris, abrupt summit plains, and the peculiar loneliness of these forms in landscapes that feel less carved than emptied. If such a truth were real, it would not need a dramatic conspiracy to remain ignored. It would need only categories. Geologists classify rocks by mineral content, age, structure, and depositional history. Paleobotanists classify fossil life by preserved anatomy. Foresters study living trees. Mining law separates coal, ore, hydrocarbons, aggregates, and timber into different legal and economic objects. Survey maps outline formations. They do not ask whether a mountain could be a chemically transformed biological remnant. Universities divide departments by method. Agencies divide terrain by resource. Once a form enters the map as sandstone, quartzite, basalt, or conglomerate, its original possibility is administratively sealed. Samples are taken to confirm lithology, not to challenge the category of mountain itself. That is how large ideas vanish. Yet are not under censorship, under routine. The truth, if it exists here, may have been hidden by inertia, classification, funding priorities, and the simple force of professional habit. Bureaucracy is often more durable than secrecy. This is where critics usually object, and reasonably so. If these structures were once biological, where is the cellular evidence? Where are the microscope slides? Where are the unmistakable tissues? The answer, if the theory has any strength at all, is not that such evidence is easy to find. It is that the processes invoked by mainstream geology are precisely the processes most capable of obliterating ordinary biological signatures while preserving gross form. Pressure, heat, silica-rich fluids, recrystallization, diagenesis, fracturing, metamorphic overprint, weathering. And deep time exposure do not leave delicate tissues waiting on the summit for casual inspection. They rewrite matter. And yet even in accepted petrified forests, original structure survives in partial, transformed ways that were invisible until someone thought to look for them. The question is not whether an exposed mountain face resembles a fresh stump under a hand lens. It is whether targeted cross-sectional analysis, isotope work, microstructural sampling, and comparative morphology have ever been designed to test the possibility in the first place. In most cases, they have not. The theory is dismissed before the investigation is defined, and there is a deeper discomfort beneath all of this. Modern civilization is built on a confidence that scale belongs to machinery, to cities, to tectonics, to industry. When evidence suggests biological systems may once have operated on scales outside modern intuition, the mind recoils. We accept giant canyons because rivers still exist. We accept mountain ranges because plate boundaries still move. But a biosphere whose ruins might be mistaken for topography threatens the frame itself. It collapses the divide between life and landscape. It suggests that some parts of geology may be cemeteries of metabolism, that forests were not merely erased into coal, but in places reclassified into stone monuments, so large we no longer permit ourselves to read them biologically. That is why the theory sounds extravagant. Not because mineralization or burial are impossible, not because catastrophic sedimentation is unknown, but because the result would force a change in scale, whilst now scale changes histories more violently than dates ever do. What remains then is not a solved case, but an altered map of suspicion. The official explanation still stands over most of the evidence, and much of that evidence genuinely belongs to it. No serious reading should pretend otherwise. But there is now another line running beneath it. Flat-topped mountains in ancient sedimentary worlds, coal measures and silicified remains below and around them. Early photographs that emphasize cut plains and vertical ribs, repeated stump-like morphology across separated regions, missing transitional terrain in certain basins, a scientific culture organized to classify by present material rather than possible original form. None of these points prove the hidden theory alone. Together, they do something more unsettling. They make the theory investigable. They move it out of rant and into method. And once a theory becomes testable, dismissal is no longer an explanation, it is a choice. So the final reframing is this. Perhaps the first forests of Earth were not erased in the simple sense. Perhaps they were processed, buried under mud, pressure, chemistry, and time. Stripped of bark, anatomy, and biological language, reduced to coal in some places, petrified trunks in others, and in a small number of extreme cases left behind as flat-top masses so large they passed through the human imagination and emerged on the other side as mountains. The form remained, the category changed, the pattern does not disappear. What changed was the explanation. And if even a fraction of that is true, then the landscape is not only older than we think, it is stranger. The real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.